start the recording. Yep, recording started. Share screen. Where were we last time? Yeah, okay. So wait, which question were we doing last time? Do you remember?
I think at around 20, let me just check. I think we were in the
22.
26th question.
22. Okay, sorry, 22 and 24 we did. Then yeah, 26 also I was saying. Yeah.
But that was a very difficult question, actually.
Hmm. Yeah, so for this I don't think there's any other way, because I mean working out the whole thing using Kirchhoff's laws. You have Kirchhoff's laws, right, in this your syllabus?
Yeah, I think we do have that, but I don't think it's implemented in this, though.
Hmm. But
That's
I
the only
mean
thing. I didn't think about
to derive this formula, you need to apply Kirchhoff's law around this thing, and then you say that okay, the current in the middle has to be zero, and then you arrive to this condition. So I mean, if you were to do that, you can, but it will take a long time, and it's only for 1 mark. That's why I was, I think I think if you just do, you have to know this relation basically. I don't think
yeah.
there's any other way. So
Yeah, I
even
don't
for
think
us,
there's any.
yeah, even for us, I think we got a lot of questions. We got some questions in the MCQ part with this thing, but this Wheatstone Bridge wasn't in our book or even in our syllabus, like explicitly mentioned. So it could be something like that here, something similar. Okay. Yes. Yeah. Okay. So that's done, I guess. Then which question did you have?
27, I think.
27. Ah, yes, yes.
Yeah.
Okay. So
This was slightly confusing one, actually, but because I wrote the opposite answer, the one with the reverse reciprocal, I think I don't know why, but it was sort of confusing me. But
hmm,
um, instead of like we are at the top or we are on the bottom, I didn't know which one should come on the top or which one should come on the bottom. I just chose the one which is the wrong one, which is the opposite
ah,
one.
right. Hmm. Okay. So it lifts the load. I think that's. Oh, wait, let me just select the pen. Yeah. So it lifts a load.
Yeah.
So that means if the weight is W is at the bottom and it's
Yeah.
being lifted to the top through, like it's lifted to some platform at a height edge. Hmm. Okay. And then potential difference across the motor is V and current through motor is I. Okay, so first of all, they're asking for efficiency. So formula for efficiency is what is equal to uh, this one, the useful energy output by total input, right?
Yeah.
Like pretty standard thing. Wait, just a second. Yeah, just a second. Just give me 2 minutes. Yeah, sorry about that. Okay, so I'm back.
It's okay.
Yeah, so efficiency is yeah, so useful energy output by total input. So you're giving some supplying some amount of energy and you're getting some output. So over here we have to identify which is what in this details that are given here. So so is energy, I'm saying useful energy output, it can also be power, right? Because I mean both numerator and denominator you can measure as per unit time, right?
Yeah.
Like in 1 second how much. It can also be power, but also yeah, it may not be power also because the time is also given. So I yeah, either way it's same thing, we'll arrive at the same conclusion, I'm sure. So let's anyway, so useful energy output by total energy input. So let's look at the numerator, useful energy output. So it's lifting weight W through H, right? So obviously and it's doing it's gaining potential energy, the weight. So useful, so this one, so the numerator will be equal to W times H, right? W is the weight, not the mass. So W times H. If you're just yeah, let's just consider energy then. So and then if you're looking at the total input, meaning the work that the energy that the motor is receiving, that is what through the circuit and whatever it's receiving V times I, right? The power
Yeah,
per unit time. It is power, and it's saying in time t. So I can so if you're looking in terms of energy, we can just call it VIT.
yeah,
So if so, then we just get E is equal to WH by VIT, right?
yeah.
I guess that's the answer. 27. Which one is this? WH by VIT. C. 27 is what? Let's check. Is it all? Yeah. Yep. 27 is C. Yep. That's that. So this one only. So which one were you thinking of then initially?
I don't know for some reason. I'm certain I was wrong in this, and I think I'm quite stupid. I chose the option A for some reason.
Uh, I mean, yeah, even I was like getting confused between these two, WHT by VI. But you have to remember that WH is already work, which means it's in terms of energy, and VI is
Yeah,
power. So you have to multiply VI with T.
yeah,
So that's why. Yeah. So yeah, I can see why it's easy to get confused, but you have to like think deeper
yeah.
at first. Yeah.
Now
Okay,
I think the
so
next question is 30.
yeah, 30, right? Ah, yes, two pendulums oscillate with simple harmonic motion. Yeah, interesting one. I had solved it, I think, on this paper.
It actually first looks easy, but actually, there are two options which you can easily get muddled up with in this one.
Hmm.
Option C and option D, which I was getting confused with.
Option which?
C or D. I was actually confused between option C or D because,
C or D, right?
uh, yeah, but I know the option was C, but I didn't know how to derive it. And why is it one less than 100 for this one?
Hmm. Okay, so I did it like this. So for pendulum A, if we consider, okay, let's consider A over here and
Yeah,
let's consider B over here, just for an instant. So pendulum A, let's say its displacement x, let's say, is equal to some it's so its amplitude, so it should be, I mean, let's just call it capital A naught, for example, sine of, then it will have some omega that's related to this, right? Like it's 2 pi by capital T. So let's just call it omega for now. And time, the time variable. And let's assign it some phase difference, phi A, for example. Okay, so we start with that. And then over here also B, let's, okay, XA, let's say. So it's XB. And we call this what, B naught sine. Oh, sorry, this will be omega A, of course, because like their time periods are different, right? That's the whole, puzzle over here, that the time periods are different. Okay, so let's say omega B T plus phi B, like that. So now, the so now the whole puzzle is about the difference between their phases over here. So this part within the sine, that whole part is called the phase angle of the oscillation. This whole thing, omega t plus phi for both, it's called a phase. So so that's why, like, when we talk about phase difference between the two pendulums, we mean the difference in phase, between the difference between the part that's in their, in their sine functions. So
yeah,
this one, omega t plus 5, omega t plus 5, their difference is what we want to know about. Okay, so in that case, we can find that difference like this. So if you do this minus this, so we get omega A minus omega B. I'm just taking t common, plus phi a minus phi b, and that, let's say, is equal to their phase difference. Like they'll obviously have a difference in phase, like throughout which varies throughout the motion, right? Let's call that just phi. Nothing, I'm not putting anything here, so it's just phi. Okay, hmm, then what did I do? Yeah, so to start out with, what we said, what they're saying is that they're released in phase. Now, in phase means what? In phase means phi is equal to 0,
Yeah,
right? They're released in phase. So at t is equal to 0, phi is equal to 0, which means what? If you substitute, if t is equal to 0 and phi is 0, that means phi minus phi b is equal to 0, right? Which means phi and
yeah,
phi b is 0. So we can, so for further calculation, we can just neglect this bit because it's a 0 anyway. So we come to the equation omega a minus omega b into t is equal to phi. Okay, so phi is equal to 0 at the start. So now what will happen? Imagine the situation. So in this case, let's say one of the pendulums is shorter than the other one. So what will happen? The shorter pendulum has shorter time period, I think. Yeah. So the shorter pendulum will go ahead of the longer one, and then
yeah,
it will come back. So so one of the pendulums keeps moving ahead of the other one in its phase. Like its phase keeps going, becoming larger than the other one. So they start at
yeah,
0. Their phases are the same, and then it and then they become out of phase, and then they come in phase again, right? Because one of them is swinging faster than the other. So how do we describe that? How do we you know describe that they are back in phase? They've gone out of phase and back in phase. So what do we call that? In the beginning, phi was 0. So we can say when they are next back in phase, what do we call it? We say phi is twice pi, right?
yeah. It's 360 degrees.
360
Of, I mean,
degrees.
2 pi.
Yeah, three
Yeah,
correct. 360 degrees. But since, I mean, over here we're in the omegas, we are calling them 2 pi by capital T. We have to use 2 pi here. We have no choice.
yeah,
So we have to use radians for this. And it's always best to use radians, because that's the standard unit for angles. So
yeah.
yes, so that's what we were. So this will be 2 pi. It can be plus 2 pi or minus 2 pi also, which depends on whether A is moving ahead of B or is B moving ahead of A, right? Because I didn't,
I think it does.
yeah, it doesn't matter. So that's why I'm saying that it could be either plus 2 pi or minus 2 pi. So, uh, so yeah, that's what I wrote here actually. Yeah, so I wrote
I
like
think it should be plus 2 pi here because A is moving faster than B. I think. Or no, I
yeah,
mean, A is
true.
moving slow.
The A is moving slower, so it should be minus 2 pi. I think otherwise we'll get a negative value for time.
Oh, yeah, I forgot that.
Yeah, then I mean, I guess no problem. But I mean, negative value of time just means that it should have happened before we started observing, which is, I mean, that's weird. But anyway, so let's say we want positive value for time only. So in that case, since 2 pi by capital T will be smaller, 2 pi by 2 will be smaller than 2 pi by 1.98. So in that case, we can
Yeah,
just say this is minus 2 pi.
yeah, that may be wise.
Yeah, so let's just call it that. So 2 pi by, let's say T A minus 2 pi by TB into time is equal to, which are two, yeah, minus 2 pi, like that. So I'll just continue working here for the time being. So yeah, what did I do? Yeah. So I can just take 2 pi in common and cancel out. So I get 1 by TB minus 1 by TA into T is equal to 1, like that. Yeah, that should be good enough. Yeah. So I get TA minus TB by TB is equal to 1 into T. Yeah, sorry. Into T is equal to 1. So T is equal to TA TB by TA minus TB, like that. So then you can substitute capital the time period of A and time period of B. So
Okay.
if you substitute, I was getting something like T is equal to 198 the time. Yeah, I can just do it again just to check. So 2 into 1.98 divided by 2 minus 1.9. Yeah, I'm getting 198 as this time here. But they're not asking for time, they're asking number of oscillations. So that means how many, sorry, number of oscillations of A
Yeah.
specifically. So not number of oscillations of B. So how many time periods of A have passed? So how many TAs have passed is what we want to know. So
Yeah.
so this time we can call it n times TA is equal to 198. So n is equal to 198 by TA. So TA was what, 2. So 198 by 2. I'm getting
Yeah.
exactly 99. So I think you were thinking time period of which one? I think, or I mean,
Yeah. I was
you're
confused
taking
with
time
that.
period of B, if, maybe that's why you were.
I don't know, for some reason I was debating between C or D,
Hmm.
and or something like that. I don't know. I was getting too confused with this one.
Hmm.
It's, I think, quite big, this question,
Yeah,
for
it
one
is.
mark.
Yeah, true. It is quite bad. So I think, and my way of working also, it's kind of like, too drawn out. You have to work faster in this. You have to like do it in, like, it's okay even if you don't think of phi a phi b and all that. You can just think, okay, omega at omega bt phi b a phi b, I don't need to bother because I release at the same time, so it shouldn't matter anyway. And uh then you just work through somehow, just like very fast, and you arrive at this. Yeah, so I mean, when you're solving it in the exam, you can leave this question till the end because if you're not sure about being able to finish it, or if you
I
can
think we
like
should do some guessing game.
huh, yeah, or like
Okay.
if you can guess reasonably well enough, that's also fine. You can just put in a guess somehow.
Yeah.
Yeah,
I would just guess 99 and I would be right. I don't care
yeah,
what the examiners
exactly.
think of me.
Yeah, and they're not asking for your working also, I believe. They just want to know if you are getting the right option or not.
Yeah.
So yeah.
That makes life much easier.
Mhm.
And
Eh,
I think the next question was 32.
yeah, and yeah, in exams also, like I mean, you don't leave MCQs blank. Do you have negative marking in MCQs or no?
No, I don't think we do have negative marking, thank goodness.
Okay,
That would be a
then
nightmare.
fine, just guess. If you're in doubt, if you like think it's one thing but you don't have time to work it out, then guess. But if you have time to work it out, definitely try it because
Yeah.
it might be interesting.
So glad it's not negative marking anyway.
Yeah.
Otherwise,
Okay.
it'll
Yeah.
be a big nightmare.
Yeah. So this one, yeah, I can understand why it would be a bit bizarre. Okay, let me just make it double page like this. Okay, yeah. So you can see both pages at once now. Right. So well, panel is driven to vibrate at different frequencies, and we're looking at amplitude at each frequency. So we are gradually increasing the frequency of the motor that's making it vibrate or whatever. So, hmm, so you're putting some kind of damping on
Yeah.
the thing. We are changing mass. So, okay. So fundamental frequency of the thing would be the same. But damping also means that the peak would move to the side a bit, to this side. The damping changes the frequency by a very slight amount, actually. So yes, in all of
Yeah.
these,
But
that
the
is.
problem was with the right two options because they both look so similar.
Hmm. Yeah, even I
Because one
was.
was more like
Yeah.
flattened out and the other one was more spiky.
Hmm. That's what. Mm, Yeah, okay, so damping, it's okay. All of the peaks are on the left a bit. And then, oh yeah, true, between these two, they're a bit confusing. Okay, can
I think I need to change my specs if I want to understand the question.
I?
Such a small difference.
Yeah, indeed. So I think you have to compare the spread. I think the thing about these amplitude versus frequency graphs is that if you put damping, there's like the graphs will kind of like be close at this point and this point. Like the peak width, how do I say? It won't be narrower or anything like that. So I mean, yeah, at low frequencies, the amplitude will be about the same, and then at high frequencies also it will be about the same. So in the middle frequency is where, you know, if you're putting damping, then the amplitude will be slightly lower. So in that
Yeah,
sense, then I think D should be the answer, which I think is the answer. If I just check, yeah,
so
32.
complicated because between C and D is so complicated. I actually chose C when I first did.
Yeah. But we're giving damping, right? So you have to remember that if you're doing damping, then the oscillator does not have so much energy to show us
Yeah.
amplitude. So that's why you cannot choose C, because then it shows a higher amplitude. That doesn't make
No,
sense.
no, actually I chose B. Sorry, I thought this was
B.
B, but B.
B. Okay. Then
Oh,
yeah.
sorry, I forgot that one. I thought that was C.
Yeah.
Oh,
So it's A, B, C, D. Yeah. So B, yeah, B, I can understand why you would choose that, because I mean the peak is lower and everything seems to be okay. But
it's just slightly different. That's what I was confused with this
yeah.
question.
Uh-huh. So that's the thing about damping. It does not change, like, it it changes the fundamental frequency only by a bit. And if you're driving, if the system is being driven, and your mass and other, like, if you're in this case, if your mass is the same, then what happens is that it, far from the fundamental frequency, it exhibits very like similar ish behavior. So that's why I would choose D instead of that. I think in the book there was a bit about it. You can read through,
Yeah,
I guess.
yeah. This is such a tough question because I was debating. I was the unfortunate C. I mean the B question and the D one. That was actually a
Yeah,
very difficult one to choose. I
yeah.
just did Inky Pinky Pong and guessed it wrongly.
Yeah. Okay, so other questions you understood, or
Yeah, I think most of the others I understood. I think. Yep.
any other
For this
doubts we
paper
can
at least.
we can discuss if you want.
I don't
Anywhere,
think I have
you know,
much more to
anywhere you're not
guess.
like sure of something or you want to clarify something, you can just.
I think these are the only doubts in this paper. Most of them were 1 marks, so that's a record.
Yeah. Okay, so you thought this also should be fine. Yeah. Okay, so if you say so, okay. Now what do you want to do? We have half an hour left.
I think shall we do electricity because that's what I think initially planned
Hmm.
for.
Okay, fine.
Because I'm so weak in it, as you saw, so many questions I was getting wrong in electricity in one
Yeah,
marks.
right.
Only one or two were outside it.
So electricity, you have specific doubts, or should we like go through the textbook, or
I think we can just go like generally because like almost like a revision type because many times I did forget like key concepts in that I'm unable to understand. It's quite difficult sometimes, particularly if it comes to the exam style questions. Electricity.
electricity as in you mean electric circuits or like electric fields? That part.
Let's run that one. Probably both, but I think we will go through the circuits first.
Okay, cool. We can do that. No problem.
Because electric fields is more like gravitational field, so I think it's not a huge
Hmm.
problem, but most of the time it's just formula
Yeah,
rather than
it is very
understanding.
similar. Yeah. Except, I mean, electric fields, you have to remember that mass, the force is, related to the charge and not the mass. And like,
Yeah.
acceleration is related to the mass itself. So that's just like small technicality. Other than that, similar only. Yeah, you're right. Okay, so okay, let me stop sharing, and then let me open the textbook and check what all is there in electricity. Okay, just a second. So in school, have you done electricity then? Or
We have done, but probably not explained so clearly because we did like a couple of like experiments and things, but I was always struggling in experiments because I can't even see how to connect resistors and things properly, and I was always getting confused with the parallels and this lost volts and things. All those things are a bit like magic.
a bit like magic. Okay,
Yeah,
so
the lost volts and all those. I just by heart the formula and just
okay, so where
I
were we?
don't think that's the best way.
It's a chapter on DC circuits, no? About when we talk
No, I think it's just general electricity. I'm not so sure. One second.
electric fields. Under fields, there is like electric fields, but you wanted circuits, so that's what I was thinking.
I think the reason you're unable to find it is because it's also first year stuff because it's put in the first year, and I think the second year stuff is that electric fields. I think if I'm not wrong. So either way, it's fine. I think.
Hmm. Okay, but circuits also you wanted to, I mean,
Yeah, just
go
like
through.
maybe you can give a little recap, maybe just for remembering,
Okay,
like
so
particularly the ones with parallels and lost volts and the hell of stuff
okay,
with that.
yeah, I can understand. When I was like in school, I was also like find it a bit weird.
Yeah,
All these things. Right, so electricity is after this, I think. Uh, am I on the right page? Yeah, direct DC circuits. Yeah, that should be it. Hmm. Okay, in fact, yeah, I can just open the textbook here. Then I can write directly there. I think that will be better. Okay, I will just share screen. Yeah. Okay, so you can see the textbook that I've shared.
yeah. I think I can see the textbook. Yeah,
Hmm. Okay, so this current rule you have understood, I believe,
yeah. I think I did understood this to some extent. Hopefully,
to some
I
extent.
do. I think it's that two laws of that strange name KIR, whatever the name
Yeah,
is.
Kirchhoff. I'll just write. It's
Can't
the
pronounce
name
that
of
name.
the scientist uh, who like discovered, who worked out these laws and like framed them. So
Very difficult to pronounce his name.
Kirchhoff is very difficult to spell also. I think something like this. I think single H or something. But either way, so Kirchhoff you can just say, and I mean most people just
I
say
think
Kirchhoff.
probably German.
Yeah, probably German. Yeah, true. So Kirchhoff's laws. So yeah, they haven't mentioned Kirchhoff here. So even they couldn't spell it probably. So yeah, so his laws are like they are applicable in all circuits. They are like they're supreme, So if nothing else, if you want to just if you want if you are like given a circuit and you're like completely at a loss, you can apply Kirchhoff's laws and arrive at the answer. Even though that way the working is probably huge. You'll
Yeah,
have to solve a lot of simultaneous equations and come to the answer. But yeah, they are. So if you're dealing with circuits where we have charges running through wires to conducting paths, then it's essential to know these laws. So first of all, you have the current law, which is that the total current leaving the junction is equal to total current entering the junction, which means effectively what? That at any point in a circuit, you are not storing charge, right? There's no charge building up, nor is there, a net charge leaving. Like there's no like no
yeah,
part of like no part of the wire of your connections or the way you've connected things. At no part in the circuit are you losing charge from somewhere or you're gaining charge and storing charge over there. So that means what? Whatever charge is entering a point in a circuit, any point in a circuit, has to leave that point. So that
Yeah.
was one, that's one fundamental thing. So in this question, what are they saying? They're saying that you you have 0. 0.5 amperes entering this junction and you have 1.5 amperes leaving this junction here, and you want to know, if I had a third connection, then how can I make this physically possible? So then they're saying, so then the rule is what? You have no charge that is being stored in here. So in 1 second, how much? You're getting 0. 0.5 coulombs of charge, and you have
Yeah.
1.5 coulombs leaving. That means in um so 1.5 coulombs total is leaving, and you only know of 0. 0.5 coulombs being supplied. So that means you have to have 1.0 coulombs supplied to this point in 1 second. So
Yeah.
that's why, so that in that way, if we work it out, then we find that wire 3 should be supplying 1.0 amperes into the point. Then we have 1.0 in, 0.5 in, total 1.5 in and 1.5 out. So that's, we are all comfortable with that. Okay, so yeah, and that's simple enough to understand. Um, so in that way, the as a like a following up point to this, it means that, no matter if you have a circuit that's connected like this, if you have one voltage source and you have any components, you can have ammeters, you can have bulbs, you can have resistors, you can have whatever, anything. Not capacitors yet. Capacitors are a bit, they have a bit of it, like you have to handle them a bit delicately in that way. So um so no matter what components we have like this, the current through all of them has to be the same
Yeah.
if you're in a series circuit, or in any like single loop of the, oh yeah, no, not loop, yeah, sorry, in a circuit like this, where you have like you don't have any branch connections like that. So uh so if you have a certain current, let's say I over here, so back here you also have to have the same current I, and over here also you'll have the same current I, and over here also I, no matter what. So that's because you're not storing charge anywhere and you're not depleting charge from any point in the circuit. So it's like, similar, you can draw an analogy with, like, you, so in your building, let's say there's a water pump somewhere, and
Yeah.
it's pumping up water to, let's say, an overhead tank or something, and from there, like, it's being distributed to different homes, and it's going out through the drainage into the sewage lines. Or no, um more simpler example, because we want to compare it to this circuit here. So I want to say that I have a pump that is like pumping up water. It's receiving water from some line here. It's pumping water out, and then, over here it's being, um it's going through a lot of, not, it's maybe running a mill or something like that, water mill or something like that, and through various different paths, and it's coming back here, and it's a complete loop. You don't have water escaping at any point. You have connected the pipelines like that. So instead of current, we can consider what? We can consider the water flow rate, or as in like the volume of water passing a particular point per second, or amount of water, or we can even say moles of water that's passing a point in a second. So in that case, at any point of the pipe, you're not storing water, nor is any part of the pipe running out of water for like seemingly no reason. So you have a constant flow of water, you have a steady flow of water. So what does that mean? That means your flow rate of water is constant throughout this whole system. No matter where you measure it, you can measure it here, you can measure it here, you can measure it here, everywhere the flow rate of water is constant. So same thing applies over here throughout this kind of a circuit. So
Yeah.
that's why we, no matter, so that's why, when we are measuring current, we say that, oh, you can just put the ammeter anywhere and you'll get the same. You should, like, theoretically you'll get the same, same amount of, same reading on the ammeter, and that won't be a problem. Hmm. So uh yeah, no, and also another thing is that if you have, even if you have a branch like that and you have something else connected here, let's say, uh either side of the branch you'll have the same current, because this is still a closed system, right? Like, you don't have charge being stored anywhere in the branch, nor you have like charge being excess, like charge, or no, you have like the branch line, you know uh having a lack of charge or something like that. You have a steady flow of charge through this system. So at this side of the branch and this side of the branch you have the same current. Okay. And inside the branch we'll come to it
So weird, because it looks
in.
more like a potential divider actually, but it's not quite.
Yeah. Yeah, not quite. I mean, potential divider, it's like, yeah, the concepts will be the same, but yeah, we'll come to that, no problem. So uh yeah, so now we can come to the potential difference rules, which is that, how they framed it. Mm, yeah, so you can think about it like this. Let's say this is some kind of a circuit. So let's and I mean, the important thing and the weird thing is that the current is considered to be flow of positive charge, even though we know it's electrons that are running in the circuit. So let's say we have our positive charge. I mean, I'm not considering electron because, I mean, but in your head, just remember it's an electron that's going the other way. So let's say we have positive charge that's coming through here, right? It's going through the battery. Now through the battery, what is happening? It is being raised to a certain potential. Your battery is supplying potential to the circuit. Same thing as, like, if you have a roller coaster, then the roller coaster is driven up the climb by a certain motor, right? There's a motor that drives has to drive the roller coaster all the way up. It's not going to go all the way up on its own. So it drives the thing all the way up, right? So it gains gravitational potential energy and then it drops. So during the drop, it doesn't need to be run by a motor because it's being run by gravity. So
Yeah,
that means it's using that potential energy to convert to kinetic. And then on the way, the kinetic energy is being converted to heat, to sound, and so on. So,
yeah,
uh, yeah. So then, so similar concept over here is that the charge is, traveling through this battery. The battery is like, uh, putting that, is receiving the charge here and then emitting it again over here. So between these 2 points it's being raised to a higher potential, and then it travels along. And of course these lines, when we are in a circuit, if we are drawing lines like this, we consider no, resistance or anything. We consider them as perfectly conducting paths. I mean, because we are doing it theoretically. In your lab, of course, your wires will have a certain resistance that you have to account for, I think, at some point. You sometimes you don't account for it. You just say that, oh, the difference between theory and experiment is because of these resistances that we didn't account for, or whatever. So yeah, so theoretically we consider no resistance. So let's see, the charge is smoothly coming along till here. So now through the resistor, what's happening? It is the charge is losing energy, right?
yeah,
It is losing energy to heat. It's colliding with all the molecules that's in the resistor, and those molecules are receiving that energy from the charge, and they're heating up. So they're taking away energy from this charge and converting it to heat. It's raising the
yeah,
temperature of the resistor. Your resistor is getting hot. So, and even in a light bulb, on the other hand, in a light bulb, what happens is that energy is being converted to light instead of just heat. Like, some of it is
yeah,
going to light and heat as well. And if you construct, if you give anything else here, let's say you put a loudspeaker here, then that's being converted to sound. So either way, you're converting electric potential energy that's being gained through here, and we are dropping that electric potential energy. We are using that electric potential energy to make the charge do work. Over here,
yeah,
if you have just resistor, then that all that work is going to heat. But if you have light bulb, loudspeaker, whatever, it's being converted to different forms of energy. So that
yeah,
is the fundamental working of a circuit. So that means like, if it is gaining some amount of potential energy here, and it is dropping all of those and coming back,
yeah,
then uh, the total potential dropped across this, it has to be the same that it gained over here. Otherwise it would be like, the otherwise your charge goes around once, then it's like, you know like, let's say it's given v naught over here. Let's look at this example. It's given v naught over here, it drops v1 voltage across this, then it drops v2, then it drops v3. So
yeah,
in each of those cases, so so your v1 plus v2 plus v3 has to be equal to v naught, because
yeah,
when it comes here, uh, it has to be at a relative, potential of 0.
yeah,
Otherwise it's like, if otherwise if it had some leftover potential, let us assume, like, why not, let's say, we are in some kind of a universe where it has some leftover potential that comes here. So after crossing the battery, what it'll have, v naught plus some amount, and then it goes again, let's say. So it'll have that v naught plus, it will receive what, it will receive again another v naught plus some amount. So
yeah,
then it would be like your charge goes around the circuit and it keeps gaining energy out of nowhere, and you're like, you cannot gain infinite energy out of that. We know
yeah,
it's not possible in real life, through like, even like, if you take physics later, then in thermodynamics, we know that a perpetual motion machine is not possible in real life. So
yeah,
we know that this is not possible. So that means, if it is receiving v naught here across this loop of the circuit, it has to drop exactly v naught in total by the time it comes back here. That's why, they we have come to this thing, this concept over here, that if you are supplying v naught through a cell, then through all of the components, the total voltage dropped has to be equal to v naught. So this is called,
yeah,
this is often, like, this one is called the emf that is being supplied. And across here we call these the potential differences. Like, v1 is one potential difference, and v2 then v3. So in total
yeah,
we say that sum of emf is equal to sum of pds. Sum of, I'll
yeah,
write pds dropped. Okay, sum of emf, I can write gained as well over here, just so we're not confused as to what they mean. Right. So, and this is true across any particular loop of circuit. Like, if you have a very complicated circuit, you can take any one loop of the circuit. Across that loop, you'll have the same story over here.
yeah,
If for example, in a circuit you don't have an EMF that's being supplied, you can put this equal to 0, and you'll get, like, the sum of PDs dropped has to be 0, because, I mean, you're not
yeah,
giving EMF, so you can't drop. There can be no net drop of PD.
yeah,
So that way, and yeah, so that way, so that's why, we can apply this across a simple loop that has no branch connections, but we can also apply it across okay, wait, that will come in a bit. But even if you have many, if you have, like, over here, let's say connect something you connect something else over here, and then you bring it back here, and then over here you've connected something something else, and then you connect something else, whatever you do, let's say you connect it like that, anything you do it, you take the PD from here and you do whatever with it. At the end of the day, when your charge goes around and like, some of it goes here, some of it goes there, some of it goes here, some of it goes there. At the end of the day, this has to be constant. This has to be true. V naught is equal to V1 plus V2 plus V3. So this is always true, no matter how you construct a circuit, or what kind of a circuit loop you're considering. Okay, so this is called the so this previous one, the simple law, was called the Kirchhoff's current law, also called the loop law as well. Kirchhoff's loop law. No, not loop law. Sorry, my mistake. A loop is the other one. This is the junction law, because we're looking at junctions specifically. So junction law, and this one is called a loop law across a particular
Yeah.
loop. So across a loop, this is the result always across any loop in any circuit.
Okay.
So this is the loop law, the Kirchhoff's loop law, or also called the Kirchhoff's voltage law. Yeah. So that's that. So then, as a consequence of this, you have this result, that the PD dropped across. If you connect two components in parallel, let's say you connect what, two ohms, and I mean, let's say 50 ohms, even you connect
Yeah.
to something like that. So you would be tempted to say that the potential that is dropped across this versus across this, you might be tempted to say that the potential drop will be different, because you're considering 2 ohms and you're considering 50 ohms resistance. It's a huge difference. Now how can you say that potential drop will be the same? But it will be, because let's say, so through here, let's say we have dropped V1 across here, and let's say, so what you have left over here is, let's not consider V2 for the moment. Let's say you have V naught in total, that EMF that you're supplying. You have dropped potential
Yeah.
difference V1. So what you have left across here is V naught minus V1, that's being left at this point. Like, a charge
Yeah.
has passed through the resistor and come here. Okay. So from this point to this point, so okay, so now let's say, we call this V2, that is being dropped across this. You know? So from this point to this point, you have to drop V2, right?
Yeah.
Okay. So let's say we didn't know what this circuit was for a moment. Let's say we didn't know what it was. It is something. We are told it is something. So across this, you have to drop uh, V2, so that your total potential dropped is equal to V naught, which is the EMF
Yeah.
that is being supplied. Okay. So now let's inspect what is this circuit element over here. So this is like two resistors, as we were saying, 2 ohms and 50 ohms. So in total, you know, so as the net result is that you're dropping V2. So now so across each branch, how much we are dropping is what we want to know. And
Yeah.
also, like, yes, across each branch, the amount we are dropping has to be V2 as well, because if you come from here, if you take this path versus if you take this path, if you if you drop different potentials across each path, then you'll have a point in a circuit where there are two different potentials, which makes no sense. Like, so over here, it has V2, so it is dropping
Yeah.
V2. So from V2, let's say, over from in this way, it drops what VA, and over from this way it drops VB. So over here, you either have V2 minus VA, or you have V2 minus VB over here.
Yeah.
But that doesn't make sense, that in one point in a circuit, how can you have two different potentials? Because electric fields, that is the property of electric field. If you have a certain uh, number of charges arranged in space, then
Yeah.
every point in space will have a unique potential, right? Even same thing for a gravitational field, right? Like, um if you are descending down a hill, like let's say you have a hill, and you're on a bike and your friend is on a bike. So let's say um you descend down the hill one path and you arrive here, and your friend takes another path and arrives here. Across the two paths, you cannot say that you have uh what to say you cannot say that your potential energy drop has been different across the two paths, because you're both at
Yeah.
the same point, and you know that a gravitational potential field is has a unique has a constant has a sorry has a given defined value, a unique value at every point in the field. So
Yeah.
if you descend down here and go here, but if your friend decides to go some complicated path and come here, you can say, oh, but the net difference in our potential is the same, is exactly the same,
Yeah.
right? Because it doesn't make sense, because at one point, if you have two different potentials, then it's kind of bizarre. Then that means that uh you could gain energy just by going through your path and then by his path or something like that. Then you're gaining, then it's like by standing, almost like you're going in a circle around the same point and you're suddenly gaining potential energy. So
Yeah.
physically that does not make sense. And it is so that's why it is like not true that that it cannot be true that across two branches like this, you are dropping different amounts of electric potential energy. Each coulomb of charge is dropping different amounts of potential energy. That cannot be true. So that's why we say that from here to here, v2 is dropped. And so like so the charge over here divides up and it drops v2 here, comes here, and it drops v2 again over here and comes here. So if you have v2 dropped across this, then v2 has to be dropped across this, and in the same way across this. So if you have a branch, uh, that means you have components in parallel. So the PD across components in parallel has to be the same
Yeah.
always. So even if you don't consider circuit, even if you consider electric fields in general, if you can see that physically it does not make sense if it were possible to drop different amounts of potentials across these two.
Yeah.
Right. Okay. So then what they have done is they basically considered these two things and arrived at this conclusion, which is what I've written over here.
Yeah.
So effectively that sum of EMF that you're gaining across the circuit is equal to sum of PDs dropped. So yeah, that those are Kirchhoff's laws. And Kirchhoff's laws, basically you just have to practice a lot of problems. I think you start with simple problems, then you go to more and more complicated problems,
Yeah.
because like they can be a bit tricky to handle, especially if you have circuits with multiple branches going on. Like this can get a bit crazy.
Yeah.
So yeah, like that. So then we can talk about, you have understood these, right? Like if you have resistor in series versus parallel, how you arrive at the effective
Yeah.
resistance.
That's actually quite easy. But when it comes to like the lost holes of something or all those
Lost
things,
holes.
it's becoming a bit crazy again.
Okay, then
Lost
let's
holes
let's tackle lost holes then for a minute. Okay,
or
let's
whatever the internal resistance or something crazy things.
okay. Yeah, I can understand. I mean, the concept is simple, right? I mean, there is a internal resistance of your EMF supplier, which is your battery in this case. Like obviously, the battery is made of like different chemicals and all that. So the charge has to travel through that somehow. So that has a certain, you know, energy that is being that so your charge has to lose some energy to go through that as well. So your cell is supplying potential, but some of it is immediately lost because of
Yeah.
that, resistance through itself. So that is the internal resistance. Like, uh, so in a circuit, that's it is shown like this. It is shown, so we have negative to positive like that, and it is shown with the resistance like this, and it is, often covered with a dotted box to say that these constitute one single component. So one point here is that even though we show the internal resistance as a separate thing in the diagram, it's actually within the battery itself. But we just
Yeah.
show it as a separate thing because then it's easier to think about it. It makes no difference. Like if you have a for a charge going from here to here, it makes no difference. So yeah,
I think one question we did was similar to this one, where I confused myself that resistance whether should be inside the battery or outside the battery, or before the battery or after the battery. I
yeah,
think we did one of those questions for the paper.
yeah. So yeah, and then I was saying that, oh no, the resistance is inside the thing,
Yeah,
inside the voltmeter. I think we are considering resistance of a voltmeter.
yeah,
So so it's actually inside the voltmeter. So that way, and then I think the way the question was worked out, it we saw that didn't make a difference. It was before or after. So same thing
yeah,
over here. You can sometimes it can be shown like this. I think it can also be shown over here. Not very sure about that, but I mean, yeah. Either way, you have a resistance and connect which is related to this battery.
yeah,
Either way. So so now our thing of lost words is, to be we have to discuss that, right? So let's say we are supplying what, let's say 5 volts here, and this is usually a very small resistance. Let's call it 0. 0.1 ohms,
yeah,
and sorry, 5 volts, this will be 0. 0.1 ohms. um, and then let's say we have some components here, and in total their resistance is like what, let's say 10 ohms for simplicity's sake. So uh, so total EMF supplied is 5 volts. You have some
yeah,
that's being dropped across here and the rest that's being dropped across here, right? Like I said, like if you call this V naught and you call this V1, if you call this V2, you have V naught is equal to V1 plus V2 either
yeah,
way, right? So um so I would say, like in this case, the circuit is simple enough. It is basically a battery with an extra resistance and along with whatever resistance you're already considering. So in that case,
yeah,
I would say just draw out the circuit and then work it out. Don't depend on given formulas. And those formulas also, you can just derive them from concepts. Like for example, you have if you want the current across the circuit, like I said, current is constant across the circuit, so we can use Ohm's law. I is
yeah,
equal to V, which is the EMF supplied by the total resistance, um, R, so which would be 10 plus 0.1, so 10.1, whatever that is. V by R originally, so that is equal to what? 5 by 10.1. So
yeah,
that will give you your I, whatever this is. So this gives you your current. That is a, and the current is the same, like over here or over here or over here. The current is the same. So we can just consider, because you can just label at any one point in the circuit, you just label it I. So just so you know that this is the current here. So you have current I.
yeah,
So you can you can look at the potential being dropped across this one. You can call it V1. So you can say V1 is equal to I times 0. 0.1.
yeah,
And similarly, you can say V2 is equal to is I V is equal to IR I'm using. That's why. So
yeah,
I into 10. So if you add these two, we can cross check our concepts here. If we uh I mean, just to like digress a bit, if we just add these two, then what do we get? We get into I into 10 plus I into 0. 0.1, so that gives I into 10.1 if we just take I
yeah,
common. So I into 10.1, that is precisely what is being supplied here at V naught. So I into 10.1 is what, if we just uh, take it from here, it's just 5. That's equal to 5, which is our V naught. So then we get V naught is equal to V1 plus V2 anyway. So even if you like wanted to check, you can always check to, you know, confirm whether you're being on the right track or not. So we've checked that, right? Okay, so let me just clean this up a bit, and we can talk about the next one. Our time is up, I think, but I'll just finish this, then we can leave it here. Okay, so you have certain voltage being supplied here with a certain
Yeah.
current. So 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 the lost volts is basically V1. So V1 is your lost volts, which is,
Okay.
say, lost volts, because this is across the internal resistance of the battery. So when you attach the battery to the circuit, like practically speaking, like in the lab, when you're attaching the battery to the circuit, you can do nothing about these volts that are being lost. They are lost. Like you can't, like, in the outside the battery, you can't do anything to, within a certain setup, you cannot, do anything about the volts. You can't get them back or anything like that, so to say. So those are your lost volts. So you can't, tamper with this resistance either, because that depends on how the battery is made in the factory, and so on. Or if you're using power supply, within the power supply, however it's, you know at the output is giving that potential. So either way, so V1 is our lost volts, and V2 on the other hand is what is available to a circuit. So I forgot the name for this. Do you remember the terms? I think I just forgot to
I'm
specify.
not good at terms very
Okay,
much.
so so effectively, V2 gets, the voltage that is, being, that V2 is the voltage that we have available to us. So this is available. I'll just write available. So V2 is what is available to us to play with in a given thing. So that way, like, and also you have to remember that V1 will also depend on the current. Uh so yeah, I think that's where maybe it gets a bit confusing. So uh so that way, you can just say V1 is equal to whatever your current is, I times the internal resistance. So R, I was right, I R int. So that's it, really. Um, and I think I, maybe they are, they're writing as I is equal to this one, R plus R int. R is this
Yeah.
one. Let's call this R. So R plus R int. So that's, maybe they're confusing you. Sorry, it will be R. Sorry, I will be what? V naught by R plus R int,
Yeah.
like that. Yeah, not that. So yes, maybe they're putting this one over here. That's why it's looking a bit scary. V1 is equal to V V naught by R plus R int times R int. Yeah. So this one, I think this is the formula you were talking about, and you didn't understand, was seeming like magic to you or something. Was it this?
Um, Also, I had just one more question. Like if you put like those what you call like another connections to the battery, like the square like thing.
Hmm.
Do you think it will become parallel or something like around the battery? For example, some in some magical complicated world, like if you just put um,
Hmm.
what you call a side connection, maybe from one point of the battery to the another, as if you're connecting a voltmeter in parallel.
Okay, so, oh, so wait, so let me just draw that. So if you're drawing it like, if you have battery plus this,
Yeah,
so this is your complete cell with the internal resistance. So you're saying you take this and you connect something across here,
yeah, and then you get
whatever.
it to the other side, maybe.
Other side meaning what? Up here?
Yeah, that's the way. Yeah,
No, but that doesn't matter, right? If I put it down or up, that makes no difference, right?
But will
Means
this be make a difference to the circuit then? Like if you did that to the upper one?
we did that to the, because you're saying across here. So let's say I've connected it here. So from here, if I were to connect something, uh,
Or
uh,
even if you didn't put anything else there, like maybe just put it blank, a blank wire maybe,
okay, blank.
with the zero resistance and
Okay, so I
resistivity or
put
whatever.
resistance and I say R is equal to 0. Same thing.
Yeah,
So, so yeah, so that is effectively a parallel connection only, no? Is it not? It will be the same thing as
because
if
R
I,
is zero.
yeah, R is 0, but I can just move this connection here, right? Because these wires make no difference. So I can just move this connection all the way here and move this connection all the way here and just connect this thing like this. So this is my 0.
Oh, it doesn't matter like if you shift this one on the top to the bottom.
Yes, so absolutely you can shift connections. That is another thing. So if you have just conducting paths, then you can then just in those conducting segments you can do whatever, as long as you don't bring it from one side of a component to another side of the component. So like
Yeah,
over here, from here to here, it is only conducting wire which has 0 resistance. So it makes no difference if I connect it here, if I connect it here.
yeah.
It makes absolutely no difference at all. So yeah, that is it. So, and also I mean you might be thinking also something like this, maybe like you have some resistors in parallel, so, and something like that.
Yeah, that same diagram which we discussed earlier.
Yeah, but let's say you have zero resistance over here. I'm not putting any resistance. So effectively it's the same thing as saying that this is just conducting wire. So you can reduce this to a point, right? So you can just call this, you can just say it's the same thing as this. But in that diagram it was not the same situation
Yeah.
actually. So so you can just construct it like this. Hmm.
So both of those diagrams are the same.
Same, but over here it had a voltmeter, and I think the voltmeter's resistance was causing a problem, I think.
Yeah, but in this case, like the two diagrams which you drew just now are the same.
Oh wait, let us go back then and just check. Oh yeah. No, but over here, one thing to consider is that you have a voltmeter. You don't have nothing in the connection. You
Yeah.
have a voltmeter. And voltmeter means there will be, I mean, the voltmeter will probably have some internal resistance and all. So I would say it's not safe to treat the circuit as if it were, just a direct connection like this. I would say don't assume that the voltmeter contributes no resistance to the circuit.
Okay.
It is kind of like you, I mean, if you know for sure, then by all means go for it. But
Yeah.
if you're not sure, then probably don't do it.
Okay.
Yeah. Hmm. Yeah, I guess that should be fine. Yeah. I can think about it. I'll try and think about it. I guess if I don't put a voltmeter, then will our answer be the same? I guess next class we can think about it then.
Okay.
Yeah. So I'll just stop sharing. Sorry. I'll just stop sharing. Okay, so next class is when? Monday, no? Third,
Yeah.
I believe. Yeah. So third, 4:30 again we can start. Okay, so bye for now. See you on Monday.
Bye bye. Have a lovely new year.
Yeah, you too.